Now, let's move on and build a project that uses the physics engine to get us going into the direction of building a game, like you will have to do for your project. To do this, the first thing we need to do is download the City engine from the Moodle page. In the resource section. I will save this into the same directory on C. And I will unzip it there. If you look into this unzipped directory now, you will see that there's a jar file, which is the actual library we'll be using, and then there's a Java doc directory, which contains documentation for the City engine. Great, so we've downloaded the City engine, but now we need to make NetBeans aware of this library. We need to tell it that any projects that will be using City engine should find City engine in that directory where we just unzipped things. To do this, we get into Tools, into the Tools menu, Libraries. We create a new library called City Engine. Make sure you don't add 40 or anything else, and you don't introduce spaces or underscores or anything like that. So it's just City Engine, and you should now see it over here. And then we go into this Add Jar option, into our C directory, into City Engine, and we select this jar file. Moreover, we also add the documentation by going to the Java doc tab and adding the folder. Perfect. Now NetBeans should know about the City Engine library. So what we will do next is we will download the first basic demo from Lecture1 and get our first game environment going. I download it, I unzip it, and after I've unzipped it, I import it into NetBeans by going to File, Open Project, and Basic Demo. Perfect, here's my basic demo project, and I can run it by clicking on the green arrow. And my very simple game environment is made out of 2 platforms and a bird character. Also, I can click somewhere on the screen in the game and produce these bowling balls. You notice how the bowling balls all interact with each other and with the bird using proper physics laws. Let's take a look at what our game contains. First of all, our game contains a world. This is an infinite 2D space in which distances and coordinates are measured in meters rather than pixels. We can populate this world with bodies. Bodies can be of 2 types, either static bodies or dynamic bodies. Static bodies are those such as buildings or platforms, immovable objects. Dynamic bodies are more like game characters that can move about. Here we are creating a ground static body and a platform static body. If we run the code, we can see these 2 platforms and we can realize they are not movable. If we were to change these two bodies to be dynamic, and then rerun the project, we would see that now the platforms fall, because suddenly they are subjected to the laws of physics. Let's change them back to being static and move on with our discussion. You will notice that our bodies are defined by these body objects or classes, but they also have a shape. Shapes can be box shapes, circle shapes, or polygon shapes. Our platforms on the ground here are box shapes because they are rectangular. When you specify a rectangular box shape, you specify its width and its height. And then you can position your box shape at a particular position in the world. In this case, 0 and minus 11.5 meters. Notice these F's, which indicate that the second parameter is a float rather than a double. So we have our two platforms, and here we make a character, the bird that you saw in the game when the code was run. Again, the bird has a bird shape and it has a body. In this case, the body is a dynamic body because we expect the bird to be able to move. And the shape of the bird is a polygon shape. Polygon shapes are collections of 2D coordinates, so each pair of numbers here indicate a point in the 2D world. And polygons can have a maximum of 8 points, and they need to be convex. So again, we created the bird out of a bird shape and a bird body. In this case, we also add an image to the bird, and we set the position of a bird to a particular position in the 2D world. Notice how we need to wrap these two numbers, which indicate meters on the horizontal and vertical axis in the world, into a vec2 object. That stands for vector 2. So now we have a world that contains two platforms that are static and one bird that is dynamic and that has an image attached to it. However, our world only exists in the computer memory, and it's being simulated. We cannot see the world unless we attach a view to it. There are several types of view that we can attach to a world. One of them is a user view, and this is the type of view that the game user, the player, gets to see. To create such an object, we need to provide the world as a parameter, and then two sizes, a width and a height, and these sizes are in pixels. So the world is expressed in meters, but when we show it on the screen, we need to specify the number of pixels that we want the size to be in. Great, and at the end we call world start, which begins the simulation of the world. In addition to the user view, which is intended for the players themselves, we can also have a debug viewer, which is intended for us, for the coders, to be able to test our environment, to test the world, and see how things work. If you run the project again, you see now that we have our regular user view, and this is what the game players see, and then we have our own testing environment. And in this testing environment, we can actually drag objects and move them around. Notice that the world is the same. We simply see it through two different views, one user view and one debug view. This concludes our review of Lecture 1. Try to do some of the lab tasks, create some interesting worlds and some physics that run in those worlds.